We're going to use dynamic balances to be able to calculate the response of concentrations, temperatures in this reactor. So we have a irreversible consecutive reactions where A goes to B goes to C inside of this. So A is reacting to B, which then reacts to C. And we have this jacketed reactor, so this might be full of cooling fluid, coolant in, and then you have a coolant out as well. And so we want to start with this this diagram, and normally this isn't available to you. So the first thing to do is just sketch it out, write out all of your variables, including the things that you want to be able to solve for, and then you'll need a separate balance equation for everything that you want to solve for. So in this case, we want to derive a dynamic model, and the things that are going to be changing here, if we just assume that it's liquid full here on the jacket, then QCN and QC are going to be equal to each other, so we don't really need a balance equation for that. But we will need a balance equation here on this reactor. We're going to need a balance equation for the cooling temperature that comes out. We're going to also need a balance equation for the concentration of A, concentration of B, concentration of C, and also the temperature. Now if we assume that Q in is equal to Q out, then we don't need a balance equation for that, but if we did, we could write a mass balance as well. So just these five variables right here. So let's go ahead and start with just the coolant out. We'll move to the concentrations. Those will all be very similar. And then our most difficult one is going to be this number 5, which is the temperature out. So when these reactions occur, they are exothermic, and so they're going to give off some heats. They have heats of reaction, delta H1 and delta H2. A couple other things that we can assume here, these reaction rates right here. So this is our reaction 1 dictated by this K1 value here, rate constant, and then we have a reaction 2 from B to C. We can also assume that the thermal capacitances of the tank contents and the jacket contents are significant relative to the thermal capacitance of the jacket walls or the tank itself. So those, we don't have to account for the temperature of the tank or the walls as well. We can just assume that those are thin and relatively insignificant compared to the contents of the tank itself. We can also assume constant physical properties and heat transfer coefficients. So we could have an overall heat transfer coefficient that dictates the transfer of heat from the jacket into the reactor contents, and so that might be temperature minus temperature C, the cooling fluid. So it just says that that is going to be constant right there. And then you might have some other properties like the heat capacity of A, the heat capacity of B, and the heat capacity of C as well. Okay, so we're just going to assume those are constants in our in this problem. Okay, so let's go ahead and start with this one first. Okay, so number 1 is going to be this coolant out. Okay, so I'm going to start with 1, and we'll just go ahead and do an energy balance. So the enthalpy of that accumulation, so this amount of fluid that's in there is going to be equal to the enthalpy in minus the enthalpy out plus, and then we'll have an exchange of heat from the reactor and the cooling fluid. So the first thing that we need to do is just say H equals M C sub P of our coolant, okay, times T minus T coolant minus T reference. Okay, and then we also have, so that's going to go right up in here, and then for our H in, okay, that's going to be M dot, or in times C sub P of our coolant times T in minus T reference, and then H out is going to be, if it's well mixed, okay, there's our coolant, T coolant minus T reference. Okay, so we're going to plug all of these up into these different terms right here. The heat transferred, okay, is going to be this term right here. So I'm going to plug in right here UA T C minus temperature of the reactor. So I always forget if it's going to be a positive or negative sign. So what I can do is always, plug in. If this is higher, if my coolant temperature is higher, then I know that I'm going to be dropping in temperature in my coolant fluid. So then I would have a negative there. So that just helps me, I always think about which one is higher and if it would decrease or increase the temperature, and then I put the sign right there. Okay, so we have this first balance. Let me go ahead and just write this out then. So we have the, let's see, maybe a density times the volume. Okay, that is the mass. And then we have a heat capacity of our coolant times dt. Okay, so that's our coolant temperature. And then let's go ahead and just the mass flow rate. So we have a volumetric flow rate here, which is Q. And so let's just assume that Q equals Qn. It's just going to be a liquid full system. And so that's going to be density times Q. And let's see, what is it going to be? So we have a temperature of our coolant in minus temperature of our coolant out minus UA TC minus T. Okay, so there is our first balance equation right here that gives us the temperature of the coolant with respect to time. And it's related to these terms. You'll notice that it's also dependent on the temperature of the reactor, how that changes with time. So we need to solve, we can't solve this equation independently. We will have to solve it with the overall energy balance for the reactor contents as well. Okay, so let's move on to number 2 now, which is our species balance for concentration A. So to do this one, there's a little bit of additional information on balance equations here at this website. We're going to do a species balance. We're going to go ahead and just grab this one. I'll go ahead and just copy this one out. Okay, and I'll paste that in here. And let's see if I can just paste it over here. Okay, so there is our species balance right there. We're going to do this for concentration of A. We have an accumulation equals in minus out plus generation slash consumption. Generation is going to be positive. Its consumption will be negative. Okay, so we are going to be consuming A because it is a reaction that goes from A to B. So that is actually going to be a negative term there. Okay, so let's go ahead and just write these terms out. We have volume is going to be constant. Then we have dCA dt. And then we'll have, let me go back up here and see. Okay, we have these terms, the CA in. Okay, CA in. And another name for V dot is Q. Sometimes we use Q or sometimes we use V dot. And that's going to be CA out, which is going to be equal to CA if it's well mixed. And then that's also equal to Q in, or we can just drop the in and just say it's equal to Q for both of those if they're equal. Okay, and then we also have the reaction rate, which was given right here. We have reaction of A, okay, is going to be equal to negative R1. Okay, and then reaction B is going to be equal to positive R1 minus R2, and then reaction C is going to be equal to positive R2. So we're going to use those later, but just remember that if you have A goes to B goes to C, and this is reaction 1, reaction 2, then you're going to have these reaction rates for A, B, and C. Okay, so the other, so we have plus reaction A times volume. So this is our second balance equation. Okay, our third one is going to be very similar. Just change CB dt. Okay, CB in times Q minus CB Q plus RB times V. Now this one was equal to R1 minus R2. Okay, and this one was equal to negative R1. Okay, and so this is our equation number 3 that we have. Now equation number 4, you can probably guess what this one is going to be. It's just going to be the same thing, but we have C here as well. Okay, N times Q minus C times Q plus RC times V, and this is going to be equal to positive R2 right there. Okay, this is our fourth balance equation. Okay, now hopefully this was just kind of a warm-up for this last one. This is going to be the energy balance for our reactor contents here. This one's going to be just a little bit trickier, but very similar to this coolant. Okay, to the coolant one. Okay, and the only real difference between this and the coolant one is that in the fifth one we're going to have some heats of reaction as well. If you remember from the problem statement, we had these heats of reaction right here. Okay, so I'm just going to do this one. Number 5, I'm going to set this one up over here. dH dt for the reactor is going to be the enthalpy flow in minus the enthalpy flow out, plus Q from the cooling jacket, plus RA times delta H of reaction A. Okay, actually we're just going to use delta H 1 plus, I'll just do rate 1 here. Okay, plus rate 2 times delta H 2. Okay, so plugging all of this in, we have D, and then we have mass times the C sub P. Okay, so this is going to be a mixture right here of the different components that we have. Then we have T minus T ref. Okay, and then dt. Let's go ahead and just sum up the, let's do this instead. Okay, let's just expand it a little bit more. We have the mass is the density times the volume. Okay, so we have, let's see, we have density times the volume, let's see, times CA. You know what? I'm just gonna do this. This is gonna be the summation of let's see, CA times the volume, okay, times the, okay, plus CB times the volume. And that's going to be the number of moles, so we're going to do a molecular weight of B as well. And let me get the molecular weight of A in there too. Of A plus C plus volume, molecular weight of C. Okay, so there's all of our mass values. And then we also have to put in here the C sub P for A. Ooh, wow, this is getting really complicated. C sub P of B, and then put in the C sub P for C as well. Okay, so you got to put the mass times the heat capacity, and then we'll have the temperature minus temperature reference there, and then divide all of that. So this is a differential with respect to time. Wow. Okay, so that didn't turn out too well. You know, let me write this out a little bit better. That's really messy. Okay, so we have D, okay, mass of A times C sub P of A plus mass of B times C sub P of B plus mass of C times C sub P of C, the heat capacity of C. Okay, and internal parentheses T minus T reference, and like that. Okay, so for each of these, we're going to have the concentration of A times the volume, okay, times the molecular weight of A. Okay, so just go ahead and do that for each of those. Okay, plug those in related to the concentrations. And then this is going to be equal to, on the right side, we're going to have the volumetric flow rates in, and we're going to have a different concentration in for each of them. And wow. Okay, so then we're going to have Q in times concentration A in times the molecular weight of A times the heat capacity of A, okay, plus Q in times, I'm just going to keep going over here, CB in times the molecular weight of B times C sub P of B, okay, that's our B right here. Okay, then plus the same thing for C as well. Concentration of C in times molecular weight of B of C times the heat capacity of C. Okay, so all of this times T in minus T. Okay, and you know what? I can't do that because I can't do those are not going to be the same amounts of each one. The heat capacity might change between those, so let's do a minus, and then you'll do this same thing, but you'll use the Q times CA molecular weight of A times CPA. So you'll do the same thing that I did here and did here, but this will be multiplied by T. I think we've got to do the T minus T ref now because they're not going to be able to be subtracted. Okay, but just replace this with CB and CC right there. Okay, so that's our outlet enthalpy, that's flowing out with the outlet stream. And then we're also going to have the heat leaving from the cooling jacket. Okay, so we have TC. Let's see if the sign works on this. I never remember if this is plus or minus. So if the temperature is hotter inside the reactor, then we would want this derivative to go down. So we would want a negative sign right there. So that is the correct sign. And then we're also going to add in delta H1 times reaction 1 times the volume plus delta H2 times reaction 2 times the volume. Okay, so this is kind of a nasty big equation right here for the energy balance around the contents inside this reactor. But that's going to be equation number 5. So let me just zoom out a little bit here and just do a quick overview. Wow, that's a lot of equations there. So we had our first equation was the energy balance around this cooling jacket. Okay, our second equation was second, third, and fourth were species balances for A, B, and C. And then the very last one was an energy balance equation for the contents of the reactor. So in terms of why we use these equations, this first one will give us TC. This one will give us concentration of A, concentration of B, and concentration of C. And this one will give us the temperature of our reactor. Now these are all linked, so we would have to solve all 5 of these variables simultaneously. And that's where you'd use a numerical solution approach like an ODE integrator in a package like Python or MATLAB. Okay, so that's this problem. We're not going to solve it per se, but just wanted to give you some experience with setting up these balance equations.